everyone, and welcome to our lesson on quantum mechanics. So just a quick recap before we get started. The main parts that we're going to see when we're working with quantum, the first part is our energy levels. So we're going to see numbers 1 through 7 describing the energy of the orbitals. Then we have our shapes, S, P, D, and F. And those shapes are related to how many orientations or orbitals. So we'll see a direct connection between S's, and they have one orbital. P's are more complicated. Those are my figure eights. They have 3 different orbitals. D's, we sometimes call this a flower shape. They have 5 orbitals. And F's are more complicated still. They have 7 different orbitals. And then in the pictures that we draw today, we're going to represent electrons by arrows. So I often will do an arrow with a half hat just to make it a bit quicker. When we do single arrows, we'll draw them in the up direction. When we partner them, when electrons share an orbital together, we'll draw the second one in the down position to show opposite spin, which is a more stable way for electrons to share a space. So the first type of picture we're going to learn how to do is an orbital diagram, also called an energy level diagram, and there's basically 3 steps. The first step is we're going to write the energy level, that's our number 1 through 7, and then our shape letters, so S, P, D, or F, and we're going to add them in a very particular order, as we'll see. You're going to draw the appropriate number of orbitals as lines above the energy level in the shape, and then you're going to draw arrows. Again, the first one always goes up, the second one goes down once electrons are sharing a space, and those will represent, of course, our electrons. So a couple of things that we'll see going further along. First of all, there's a very helpful tool, and I'm going to use a picture of it in our lesson today, and that is a schematic on page 188 that shows us the order of how electrons fill orbitals. And as we get lower in the periodic table, we're also going to notice there's a bit of a detour. If you look at the actual numbers of the elements, you're going to notice that we have a detour after 6s. We go into 4F and then 5D, so that's one set of detours, and then the 7S detours to 5F and then back up to 6D. Now, right now, without a whole lot of context, we don't have a whole lot of concept of what I'm talking about, but we'll see this come into play a little bit later on. What we will see up front, though, is valence electrons. So valence electrons, remember, are the ones in the outermost shell, but we see them a little bit differently in quantum. Quantum, the way we identify them, are all electrons in the highest numbered orbitals. So the energy levels are my numbers. For instance, above, if I look at this example here, if I had electrons in the 7s, the 5f, and the 6d, if I were identifying the valence electrons, it's the ones in the highest numbered orbital, and in this case, the highest number is a 7. So the highest numbered orbital electrons would be the ones in the 7s. Those would be the valence electrons. If I had more than one orbital with the number 7, I would count all of the electrons in all of the orbitals with the number 7. With the 2 towers on the periodic table, so the tower to the left and to the right of our transition metals, we can still use column numbers to actually predict column number or valence electrons. So we'll be able to do that same thing that we did with Bohr-Rutherford diagrams. We'll do it with quantum as well, which is pretty handy. We can check our work. So this is the schematic. So again, you'll find this on page 188 of your textbook. And this shows us how we have to order the electrons. So just like there was a plan when we did Bohr-Rutherford, we had 2 electrons that fit in the first orbital, then 8, then 8, then 2. It's a similar type of process. There is a plan of how electrons go into the orbitals. But because there's so many more orbitals and they're more defined, we have to have a more elaborate plan. So this is our plan, and we start from the beginning, which is our 2s, or 1s rather, right here. And so I'm going to use this tool to help me figure out electron placement. I'm going to read it like you would read a book in North America. So we would start from the top left of the page, we would go across, and when we get to the end of the row, we then go down a row. Same sort of thing when we work with this tool. So let's jump into an example so you can see how this is done, and we'll go through this first one with oxygen. So I always start by drawing the symbol for my element and some colons just to say this is the one that I'm looking at. We're going to draw an orbital diagram for oxygen, and then we're going to circle the valence electrons. So again, we're going to use this tool, and it's going to help us figure out where we're putting electrons. Just like when we do Bohr-Rutherford diagrams, we put electrons in one at a time. Same thing if I'm doing a quantum orbital diagram. I put in electrons one at a time, and they have a very particular location. So I'm just going to be identifying where those electrons are going. So the first orbital is called a 1s orbital. 1 is the energy level, s is the shape, so it is a sphere. S's have one possible orientation or orbital, so then I draw a line to represent that orbital just on top. Now it's time to put some electrons into this orbital. So similar to Bohr-Rutherford, at this point I would have drawn a circle. This time it just looks like a line. So I would draw my first electron as an arrow in the up direction. Now if I left the picture like this, this would represent an element with one electron. So what I've done is I've actually drawn, I'm just going to put a strike through it up here, I've drawn a hydrogen. Now I'm not done yet because I want to get 8 electrons in total for oxygen, so I'm going to continue to add more electrons. Well, it just so happens that every orbital can hold 2 electrons, so there's space for another electron here. And if I look at my plan, my tool at the top here, if I have filled this 1s and I'm reading across like a book, the next electron is also supposed to go in the 1s. So I'm going to put it in going in the opposite direction. I'm going to cross that off to keep track here. I've now filled my 1s, and I've gotten to the end of this row, so I'm going to go down a row to figure out where to go next. So the next thing to draw is a 2s according to my tool. So 2s is the next orbital. Again, an s is a sphere. It has one orbital or one orientation, so I'll draw one line to represent that. And then I'm going to put an electron in, and that will be the very first one. That's lithium. And then I'm going to put in a second one to fill it, and that one will be beryllium. And now, once again, I'm out of space, so using the periodic table here, I can read across and see where I have to put electrons next. Next, I'm going into the 2p. So I'll label the orbital. P's, remember, have 3 orbitals. 1, 2, 3. And I'm going to put an electron in here for each element as I get towards oxygen. So the first one is boron. Then we've got a carbon. Then we've got a nitrogen. This is Hund's rule that I'm using right now. I spread my electrons out first before partnering. That's a rule that we always use. They would prefer to have their own space if they can. And now I get to oxygen, so now I will have to partner. So I'll put a 4th one here. So there's my orbital diagram. Now I'm going to do the second part of the question, which is to circle the valence electrons. So again, my valence electrons are electrons in the highest numbered orbital. The highest number here is a 2, and there are 2 s's and 2 p's. So everything in the 2's is going to get circled. So I have 6 valence electrons here, which makes sense because oxygen is in the 6th column, and as we know, the column number tells us valence electrons. So we can check our work that way as well. Let's try another one. This time we're going to do iron, a little bigger. I'm going to start off the same way. So I'm going to draw my symbol in my colons, and then I'm going to start right back from the beginning, which my first orbital is a 1s. Again, the s has one orientation or one orbital, so I'm going to draw one line to represent that place for electrons. First electron goes in the up direction. There it is there. I'm out of space, so I go across to the next orbital, and it's telling me, oh, you're not done yet. Fill that 1s a second time, which makes sense. We don't make a new orbital until we fill the last one. Now I'm out of space, so I'm going down to the next row. I'm into that 2s. Again, s is a circle. It has one orbital, one orientation, so one line. Here's the electron for the next element, and the next. So that's nice and filled. I'm going to keep going over to that 2p now. P's have 3 orbitals, and again, I would spread them out before partnering. And that takes care of those elements there. And now I'm into my next row, which is a 3s. S. Again, S, one orientation, one orbital. There's electrons 1 and 2 there. Then I'm coming across to 3p. 3 orbitals for p. 1 electron per element. That'll take me all the way to the end since I've got 6 elements there and 6 electrons to put in my p. Then I'm into that 4s. S again, 1 orbital. 2 electrons there and there. And finally I'm into that 3d. I'm out of space, so I like to just work lower down if I've run out of space, and you can do the same thing. D's have 5. We haven't seen those yet. And here we're going to slow things down a little bit because we're going to count the electrons to get us out to iron. We're now into that orbital that it contains our element. So our first one goes in. There's our second electron. That's third electron there. Chromium is the 4th. Manganese is the 5th. And iron is the 6th, which means we will have to partner once there. So there's our orbital diagram, and let's do the second part. Let's find those valence electrons, again using the definition. So our valence electrons are highest numbered, which means the 4s electrons will be our valence electrons in this case. The next one here is a you try it. So this means you're going to pause the video, attempt it on your own, and then press play to see how it's solved. Pause the video now. I'm going to show you how to draw this one, and you can check your work. So I'm going to do an orbital diagram for silicon, element number 14. So starting off as always. So I've got a 1s, 2 electrons there, 2s, 2p, 1, 2, and 3. From here we have a 3s and a 3p. And there are 2 electrons until we get to silicon. And now I will circle my valence electrons. My highest number is a 3. Everything in the 3 gets circled, so I have a total of 4 valence electrons, which again makes sense since silicon is in the 4th column on the periodic table. So let's switch gears and do a different style of picture. This one is called an electron configuration, and this one has only 2 steps. The first one is to write the energy level and shape letter, just like we did when we did our orbital diagrams. But this time, instead of drawing arrows, we're going to write the total number of electrons in that orbital as a superscript or an exponent. So let's have a look at our first one. We are looking at technetium, which is element number 43. The symbol looks like this, Tc. And again, we're starting from 1s. So we're going to draw the 1s, and then we're going to count how many electrons would fill an s. And I'll just remind you, s's have 1 orbital. Each orbital holds 2 electrons. 1 times 2 makes 2. So we'll do a superscript. Now, if ever we couldn't remember that, we can use the periodic table to help us. You'll notice that in the s block, there are always 2 electrons, 1 for each of those, or sorry, 2 elements, 1 for each electron that fits in the s. The next one we are going to is a 2s. And again, an s is 1 orbital times 2 electrons. And now over to a 2p. P, remember, has 3 orbitals, 2 electrons each. 2 times 3 makes 6. Again, if you couldn't remember that, you can count how many electrons are in any of the p's, and there are 6 elements out there, which means 6 electrons, 1 for each. Let's keep going. From 2p, again, we're right here. We're just going to keep going. So now we're in 3s. S's can hold 2. Going across the divide, we're now over to 3p, which holds 6. We're going down a row now, so we're into 4s. And s's again are 2. Now we're into 3d. D's, remember, have 5 orbitals, 2 electrons per, so 2 times 5 makes 10. And now we're continuing across to 4p. Again, we're a 6 there. Now we're down a row to 5s, 2. And finally, we've got 4d. Again, we're going to take our time and count how many elements it takes us to get to technetium. And it takes us 5 elements, which means 5 electrons. So there is an orbital diagram for technetium. Let's circle those valence electrons. In this case, my highest number is a 5. So the 2 electrons in the 5s orbital will be my valence electrons. All right, this is a you try it. So once again, you're going to pause the video, do the question yourself, and then press play to see if you got it right. I'm going to solve it for you now. So this is strontium, Sr. And again, we're starting from 1s. So we've got 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10. How far do we have to go here? Oh, I went too far. Hold the phone. Back that up. Fix that. All right. So, yep, we're going to end with our 5s2 here. And again, circling my valence electrons, my highest number is 5. So this will be a 5s2. And there's my solution, a little bit nicer typed out there. All right. Now, let's think about if we had to do something with far more electrons, isn't there a more practical way to do this? The answer is yes. We can do something called an abbreviated or shorthand version of these pictures, either the electron configuration or the orbital diagram. The way we do this is we use the preceding noble gas, and this just means the one that comes before our element. So we would go up a row, and then remember the noble gases are the last column on the right. So we're looking for that noble gas, and basically what we're going to be doing is we're going to start with the noble gas as a symbol, and what we're going to say by putting the noble gas symbol in there, we're saying this element looks like this noble gas plus this extra stuff. So we're just going to build from the noble gas. It'll save us all the way going back from 1s. So this allows us to do much bigger pictures. So let's do this first one. This is an electron configuration of iodine, number 53. So again, I'll start off the same way with iodine, and I'm just going to use my periodic table. I'm just going to circle my iodine, and 1, 2, 3, 4, there it is there. And so I'm just going to circle the preceding noble gas just so you can see where you're looking. So you're going up one row, and then again it's that last column. Those are my noble gases. So we're looking at that one there, and that is going to be krypton. So we start by writing krypton, the symbol, in square brackets. Now what we're going to do, we're right here, and we're just saying, okay, iodine looks like krypton plus this extra stuff. So we're going to build the picture from krypton. It just saves us going all the way from the 1s because they would look identical for the first 36 electrons, which is how many electrons krypton has. So now we're just going to build from there. So we're in the 5s. This is an electron configuration, so 5s2, then our 4d10, and then 5p, and it takes 5 electrons to get out there. Let's circle the valence electrons. The highest number here is a 5. And I see it twice. I see it here, and I see it here, for a total of 7 valence electrons, which makes sense because iodine is in the 7th column. Let's try another one. So this is an abbreviated orbital diagram this time of platinum. So we start with PT. This is element number 48. So let's just identify it on the periodic table here. Platinum, I've just circled it in the 5D block, and so we're going to go up one and to the end to identify the noble gas that we need. So the noble gas we need is going to be xenon if we use our proper periodic table to identify it. And now we're just building from 6s. This is an orbital diagram, so we'll start with our 6s here. And this is where I mentioned it before, but we haven't really seen it until now. We are now going to have to take a detour. If we have a look at the 6s, the last element here is barium. And barium is element number 56. Well, if we look at the element starting in the 5D, that's element number 71. Well, I don't know about you, but that's not how we count. Element number 57 is right here, which means after the 6s we have to detour down to the 4f. Now they didn't they took this block out of the periodic table so it's more manageable on a piece of paper, but in actual fact, the S should be pulled to the left, and the F block should actually be shoved in between the S block and the D block. Because we don't use the F's very often, they get pulled out and the periodic table gets pushed together, so it's a little bit more manageable for most things. So let's remember this detour, and we're now going down to that 4F, and F's have 7 orbitals. 1, 2, 3, 4, 5, 6, 7. We'll fill these up. We can fill quite quickly until we get to the very last orbital, because just like Bohr-Rutherford's, we fill until that last orbital, so we can quickly fill things until we get to that last one. Now we're going to go back up to where we left off before that detour. We're in the 5D zone. 1, 2, 3, 4, 5 orbitals for a D, and then we're going out until we get to that platinum, which will take us to 8. 1, 2, 3, 4, 5, 6, 7, 8. Again, we're just going to count from the beginning, and we're just going to count each element gets 1 electron until we get to platinum, and that is 8. In terms of circling valence electrons, highest numbered is a 6. So we have got those 2 valence electrons in the 6s. All right, this is a you try it. So again, you're going to pause and then play to check your work. You're going to draw an abbreviated electron configuration for dubnium, which is element number 105. So pause now and then play to see how you did. I'm going to solve it for you now. So dubnium is Db. And again, it is down in this bottom row. So we're just going up 1 row to figure out the preceding noble gas, and that is going to be radon, Rn. Oops, that's a funny looking N. Forgive my N. And then we're continuing from radon, so 7s. This is an electron configuration, so 7s2. And just like before, the detour is going to occur. After 7s, we go down to 5f. And there are 14 electrons. Again, if you couldn't remember there's 14 electrons, you could count the number of elements in the F block. There are 14 elements, which equals 14 electrons. Then we're continuing into, whoopsies, I need my number first. We're continuing into that 60. And we're only getting 3 electrons until we are done. And then my circling of valence electrons would be the 7, the 2 electrons out there. And there's my proper solution with pretty typing. All right, let's finish off with 2 last ideas. The first one is ions. So ions, remember, there are 2 types. We have our anions, which are negative, and this is when electrons have been gained. We're going to add those extra electrons to the last orbital where there's space, so that makes sense. The cations are my positive ions. These are my valence electrons, which are going to be lost. Remember, my valence electrons are highest numbered orbital or orbitals. And this is probably where we have the most issues, is because we take the electrons out of the last orbital, but remember, the valence electrons are not always the last. We've just practiced circling those orbitals, and you can see a lot of times they are not. So when we're removing electrons, they're coming from the highest numbered orbitals. Very important. Also, we want to make sure we remember that gaining is negative and positive is when we lose electrons. It's often easy to mix those things up because we often think as negative as a losing and positive as gaining, but when it comes to electrons, remember, electrons are negative, so I become negative by gaining electrons and I become positive by losing negative electrons. All right, the anions are definitely a little bit easier, so let's start with nitrogen. We're going to do a nitrogen 3-. This is an orbital diagram. That means I'm going all the way from 1s. I don't use the word shorthand or abbreviated here, so that means start from 1s. So 1s, 1 orbital. There's my first 2 electrons, and then we're going to 2s, 2 electrons, and then 2p. I'm going to start by doing nitrogen. Nitrogen has 3 electrons, but 3- means that I have gained 3 electrons. So I'm just going to add them where there's space in the last orbital. 1, 2, 3. And you can very easily see why nitrogen would want to gain 3 electrons, because now, if I circle my valence electrons, I now have 8 valence electrons, which means I look just like a noble gas, which means I'm stable and I don't have to work anymore. So that's exactly why nitrogen is doing that. Let's try, and cation now, and we're going to do lead. This one is an abbreviated orbital diagram, and so lead is just about, where's lead? It's about here-ish. And so our preceding noble gas will be up here. We'll start with lead as a normal, and then we'll deal with the 4+ charge and what that means. So again, we're doing an abbreviated orbital diagram. We're going to start with xenon, and then we're continuing here into the 6s. So this is an orbital diagram, so 6s, 2 electrons. Don't forget our detour, 4f, 1, 2, 3, 4, 5, 6, 7. I'm going to try to keep them small so I can fit them all in here. Ooh, getting a little crazy on that one. Then our 5d, 1, 2, 3, 4, 5. Fill that up. And then we're into our 6p, 1, 2, 3. And it's 2 electrons to get me to lead. So that's what lead looks like. Now let's apply that 4+. So again, in order to become positive, this means I lost 4 electrons because electrons are negative. I'm taking them from the highest numbered orbitals. I need to get rid of 4 in total. So I'm going to get rid of both of the electrons in the 6p. Highest number here is 6, so that's where they're coming from. I still need to get rid of 2 more. Again, highest number is 6. I'm coming over for those ones. Notice that I've left behind the 4f and the 5d orbitals. They're nice and full. That means nice and stable. So that's why lead can lose 4 electrons and still be stable. Lead also likes to be a 2+ charge. So when we think of those multivalent metals from grade 11, if I only took the 2 electrons in the 6p, that would make it a lead 2+. But you can see by losing 2 or 4 electrons, lead can be stable in both ways. And that's why transition metals often have more than one possible way to become stable. All right, this is a you try it. You're going to be doing this one. This is Zn2+, zinc 2+, electron or element number 30. So you're going to try it, and then you're going to come back and have a look and see if you're right. I'm going to solve it for you now. So we've got Zn2+. We're going to start with zinc. Zinc is just here. And the preceding noble gas is up here. That's argon. So I'm going to do my, why can't I make a dot? Forget that. Okay, so from argon, we're coming across, and we are in the 4s, 4s2, and then 3d. Normally that's a 10. Because it is a 2+, that means we are losing 2 electrons. And again, they have to be from the highest numbered orbital. So we're going to take the 4s2. Just like I've shown you in the last 2 examples, I'm just putting a strike through the electrons I want to get rid of. That's completely fine. You don't have to erase them. You can just put strikes just like me. All right, the very last thing we want to go through is something called the weirdos, or unexpected electron configurations. This only applies to 2 areas on the periodic table. It applies to the column that starts with chromium at the top and every element in that column, and the other column is our copper. And what happens here is one of the electrons from the last s orbital will actually go into the last d shell. And it automatically happens. It just equals greater stability, and all elements do things that are best for stability. So let me show you how this works, and then we can explain it. So let's do an abbreviated orbital diagram for copper. This is what you would expect copper to look like, but it will automatically take 1 electron from the s, get rid of it, and put it over here. Because a full 3D is more stable than having a full 4s. So again, it just automatically happens. Your job is to remember that it happens and to look out for the weirdos. So they're not going to have a flashing sign saying, hey, I'm a weirdo. They're just going to stick in there. So you're going to have to look out for these columns. And that is this column here. And that is this column here. 1, 2, 3, 4. Those 2 guys. Watch out for them. I'll show you one more example of a weirdo. This is the example of the group under chromium. This is molybdenum, which is right under chromium, but they all work the same way. What ends up happening, just like the last example, is one of the electrons will leave the s and come over. Whoopsies. Ignore that one. It wasn't supposed to be there. So one of them will come over from the s, and it will come and populate the d. And again, that's because one electron in each of the orbitals of the d is more stable than 4 and an empty orbital. And because it's more stable, it will automatically happen. And that's a wrap, folks. That's quantum.